These notes are part 2 in the lecture series on solutions. This is going to be about the saturation degree of solutions and how the colligative properties of solutions can be affected. In the previous lecture we talked about the different parts of a solution, meaning the solute and the solvent, and we talked about what makes a solution a solution. So what causes dissolving and dissolution and dissociation, and what are the forces of attraction that are that affect whether a substance will dissolve or not. So in this lecture we're going to consider all solutions that we talk about as having dissolved, meaning that we follow the like dissolves like rule, and the forces of attraction between solute and solvent are greater than that between the solute and solute. So all solutes we're going to refer to here are easily dissolved in the particular solvents we talk about. When looking at a solution, you want to talk about how much solute is dissolved in the solution. There are 3 ways you can describe that solution. The first way is saturated. Saturated means full. So a saturated solution is describing the solution that is full of solute. It contains the maximum amount of solute that can possibly be dissolved, and it is very important to note that that is at a specified temperature. The temperature of a solution affects how much solute can be dissolved. So when you're referring to a saturated solution, for example, if you say that 100 grams of water can hold 100, well that would be too many, but 100 grams of water can hold, say, 20 grams of sugar, you have to specify at 20 degrees or 30 degrees. Because as you'll see in a minute, if you increase the temperature of the solvent, then more solute can be dissolved in it. And it has to do with as you boil or increase temperature, the kinetic energy is greater, and that means that there's more space between the solvent molecules, so the more solute can fit in between. If you have a solution that contains less than the maximum amount of solute, again at a specific temperature, then that is referred to as an unsaturated. So saturated means full, unsaturated would be the opposite, which means not full. When you're looking at a saturated solution and you want to talk about how much substance is in it, you can talk about the solubility of that substance. So we used the word soluble in our previous lecture. Soluble meaning a substance dissolves in a given solvent, so if something is water soluble, it will dissolve in water. In this case, we're talking about solubility as a measurement. So solubility is the amount of a solute that you can dissolve per volume of solvent. And again, this is at a specified temperature because the temperature affects how much will dissolve. So in the graph you see below, we're looking at solubility in terms of grams of the substance we're looking at different salts, and the volume is 100 grams of water. And again, this is by different temperatures. So if we were to look at table salt, sodium chloride, we would see that at 0 Celsius, only, let's say, about 35 grams of sodium chloride can be dissolved. However, at 100 degrees, if you have warmed that 100 grams of water up to 100 degrees Celsius, you can now dissolve about 40 grams of salt. So in general, increasing the temperature of a solvent will allow more of the solute to dissolve. So that is why it is very important to specify the temperature. Now if you have a solution that has more solute dissolved in it than the maximum amount, that is called a supersaturated solution. And this occurs when you have a solution that you warmed up to a high temperature and dissolved a maximum amount of solvent. So you made a saturated solution at a high temperature, and then that substance cooled off. As the substance cools, the excess solute that was dissolved will precipitate out of the solution. This word precipitate, it means the substance will go from an aqueous, meaning in its dissolved form, to a solid. And we're going to look at a picture of that right here. In this YouTube posting by Dr. Freudiger, he's showing a supersaturated solution of sodium acetate. This is also called hot ice because, as you'll see in a minute, the crystal that's formed looks like it's ice, but if you were to feel this flask, it would be very hot to the touch. So as you'll see in a minute, he is going to add 1 piece of solid sodium acetate, and as it falls into the supersaturated solution, it is going to cause the solution to form precipitate. So this is a supersaturated solution, meaning there is more sodium acetate dissolved in this water than there should be at this temperature. So he did this by warming up the temperature, warming it up, dissolving extra sodium acetate, and then letting it cool off. So when he adds this extra, what's called a seed crystal, when he adds this one little bit of solid sodium acetate, it's going to cause the remaining excess sodium acetate that is in the solution to stick to that seed crystal and basically form a giant crystal cluster. And then you'll see that the whole flask gets filled. So we can see that the seed crystal was just dropped, and now you can see these long spires of crystal forming, and they went down and it bounced off the bottom, and they're bouncing off the sides. So what's happening is this is almost turning into a big solid because the solution has basically turned into a big solid because the solution has allowed all the excess solute, the sodium acetate solute, to form out of the, basically fall out of the solution. So the sodium acetate has precipitated out of this solution, and we have seen that as crystals. If we know the solubility of a substance, then we can actually predict how much solid will precipitate out. So for example, if we're looking at sodium, this is sodium nitrate, and say we warm up our sodium nitrate to, let's say right here, which would be about 40 degrees, and we're allowed to put in, that will allow us to put 100 grams of sodium nitrate into our solution. And then let's say we let it cool off to room temperature, which is roughly 20 degrees Celsius, in which case only 90 grams can be dissolved. So the difference between these two would be 10 grams. So 10 grams roughly is going to precipitate. So at 40 degrees, a solution made of 100 grams of sodium nitrate in 100 grams of water is saturated. However, if you then keep that 100 grams and it is at now 20 degrees at room temperature, that is now a supersaturated solution, because only 90 grams should have been dissolved, but there are 100 grams dissolved in it. So you could force that solution to then have a precipitate form. So again, a supersaturated solution forms by having a warm solution. You add the maximum amount of solute, and then you let it cool off. On to colligative properties. A colligative property is a property of a solvent or a solution that can be affected by the concentration of solute that is in it. So for example, boiling point and freezing point of a substance can be affected by adding solute to it. Now, the identity of the solute is not important. So for example, if you are adding salt or if you are adding sugar, that is not important. It's the amount of solute that determines how much the property is affected. So if you were adding 10 grams of salt or 10 grams of sugar, that won't make a difference. What is important is that you added 10 grams. So let's look at freezing point and boiling point and how they are affected. Let's look at an explanation. Boiling point can be elevated by adding solute. So what that means is that if you were to look at this graph here, and we're looking at pure water is with 0 molals. Molality is a measurement of concentration. So at a 0 mole solution, water is going to boil at 100 degrees. However, if you look at a solution that has now 6 molals of sugar, that's going to raise the boiling point by 3 degrees. It's now going to boil at 103 degrees. So as you can see, the greater the amount of solute that is added to, in this case, water, the higher the boiling point is. The reason for this is that when a substance is trying to boil, it is trying to break this barrier here between the liquid phase and the solid phase. If there are solute molecules or particles in the way, then they're going to be in the way of these molecules that are trying to break this barrier. So for example, this molecule here is going to bounce off of this solute particle and go back in. So it takes more energy, which means more heat, at an increased temperature in order for these solute or solvent particles to go from a liquid to a gas. Similarly, freezing point can be lowered. So this is called freezing point depression. And again, by adding solute, you're going to cause a solution to freeze at a cooler temperature than it normally does. Pure water, as we know, freezes at 0 degrees Celsius. If you were to add, let's look at 6. If you are to have a solution at 6 moles of sugar, then it's going to depress down to, looks like about 11 or 12 degrees Celsius. So it's going to depress the freezing point of the water down to 12 degrees. So the more sucrose, or in this case the more solute you add, the lower the freezing point of the liquid will become. This is similar because you are, in this case, what is the problem is that these liquid molecules are trying to form strong intermolecular forces with the neighboring molecules. So if they're going from a liquid phase to a solid phase, they're trying to form basically like a lattice or a crystal structure. And these solute particles get in the way. So for example, this molecule now cannot form an intermolecular bond, or in this case it'd be a hydrogen bond, but with this molecule, because there is this solute in the way. So the substance is going to have to get at an even lower temperature so that the molecules get even closer together and have even less kinetic energy, less vibration, in order for them to reach the full solid phase. In this animation from Iowa State's chemistry department, we can investigate boiling point elevation and freezing point depression. So imagine that this is a lab where we have a heating apparatus, and we're going to add a certain amount of, in this case we're going to choose sucrose, and we're going to add it to 100 grams of water. So if we were to have 0 grams of sucrose, meaning pure water, and we lower that sample in, if the probe was in it, this data here is telling us that water typically boils at 100, freezes at 0. It's freezing and boiling constant, which you'll learn about in AP chemistry. Have these numbers, you don't need to know those. But we find that it is boiling at 100 degrees just like we expect. And if we look at what's going on in the microscopic view, we can see that the molecules are moving around, and they are moving from the solid to the liquid, or I'm sorry, the liquid to the gas phase. So let's reset this, and let's instead add about 6.4 grams of sugar. So we now have that on our little scoop here. So again, we have our data, but let's look and see what temperature it's going to boil at. So water boils at 100, but we have added 6 grams of sugar to that. So knowing what we know about adding a solute, we expect the temperature to go up, and as we see it does. We see that we now have bubbles forming, so this is boiling, and it's boiling at just above 100 degrees. So I would expect if we were to double the amount of sugar or greatly increase it, then we would have a much higher boiling point. If we look at the microscopic view, we see that the orange particles, which are the sugar, are causing the some of the water molecules, which are trying to escape into the liquid, into the gas phase. They're bouncing off of the sugar that's in there. So it's going to have to be at a much higher temperature. It's going to take longer for the water to boil. So let's reset this, and let's put it on cold so we can look at freezing point. Let's look at, if we keep that same amount of sugar, how is that going to affect the freezing point of the water? So knowing what we know about water, we expect it to freeze pure water at 0 degrees. However, adding a solute we know causes freezing point depression. So we expect this to freeze solid at less than 0 degrees. And as we see, it's around negative 30 degrees that we're getting our freezing point. So the sugar has greatly depressed that. On the microscopic level, we can see why. As these water molecules are trying to form intermolecular forces with the rest of the water crystal, the ice cube, these sugar molecules are getting in the way and preventing that. So it takes more time and the removal of more energy in order for the substance to get frozen.